Okay, so I am SRIPAN. I am working at at ITBHU as a PM scholar, and this is the fifth week of this live session for this course Fluid Dynamics for Astrophysics, which I am taking as one of the deliverables towards the PM scheme. So today, as usual, I will discuss about 9 to 10 MCQ or objective type questions which might be helpful for the people who have joined or registered for this course to solve the assignments given to them. So this is our first question. So we have a just a second. Okay, so the coding, yeah. So one second. Yeah, so we have our first question here, that a pressure perturbation is generated within a gas flowing with a velocity u. So the perturbation has a velocity equal to local sound speed. So as we know that if there is any pressure or density perturbation within some gas which does not have any magnetic field with itself, then the pressure perturbation will move with the speed cs with respect to the gas flow itself. Now the speed of propagation of this perturbation as discerned by Lagrangian and Eulerian observer will be. So we will have four options. So first of all, we may remind ourselves that what is the Lagrangian frame and what is Eulerian frame. So let's say you have a flow of liquid, and if you are an observer who is sitting just on the fluid and moving with the fluid, so what you will find out that any change in any quantity of that fluid associated with that fluid, that should change only with time. There should not be any change. I mean, there has to be some change, but you would not feel any change due to any change in the spatial location. So now what and Eulerian observer is a lab frame observer. So you have a fluid and you have given some perturbation, but what Eulerian observer will see is if there is any velocity of the flow itself, or addition to that, if there is any velocity associated with the pressure perturbation itself. So now with this much concept, if we try to find out this answer, so Sumit, can you tell me what can be the answer for this question?
I think the answer will be number 1, CS plus U and CS.
So Lagrangian observer is that observer who is flowing with the flow itself. Okay. So
Okay.
now
No, then that is not 1.
Yeah. Now tell me.
It will be number 4. It will be
Number
CS
4.
and
Yeah.
CS comma
Right.
plus minus U.
Correct. So for this question, the answer will be number 4, because as I discussed that if the observer is itself moving with the flow, he or she cannot predict or cannot find or feel the velocity of the flow itself, as he or she is also moving with that particular velocity. So what she feels about the velocity is only the velocity of the pressure perturbation which is moving with the flow. So, and in this case, the velocity of the perturbation is the CS, the propagation of perturbation. And the Eulerian observer, since he or she is a an observer in lab frame, so he or she will feel both the velocities. Now depending upon the direction of the CS and U, so we could have plus or minus sign. If it both of them are in the same direction, then we will find out that it is CS plus U. But in which case that the flow is moving let's say in left direction and the perturbation is moving in right direction, then we could find that CS minus U also. So considering everything, we will find out that the fourth option is the correct one. Now let's move on to the next question. Okay, just a second. Let me write down the answer also. Answer is 4. Now the next question is, so we have 2 points P and Q within a gas flowing with a constant velocity V. So what we have is, we have some constant some fluid is flowing with some velocity which is constant at each point, let's say V. Now even though P and Q are not very far away, so what the question is telling, let's say you have a P point here and you have a Q point here, right? Now it is saying that these points are very much close to each other, but still the pressure perturbation generated at P cannot reach Q ever. So choose the correct option. So let's say, so what we have, initially you have a gas flowing and now you have perturb. So the perturbation is also moving from one point to another point. So you have both the velocities, you have a V, you have some CS speed with which the pressure perturbation might move, which is CS. Now the question is asking that whatever if the 2 points are very much close to each other, then also this P, the perturbation in the P cannot affect the Q point. Now how can that happen? That can only happen if the velocity of the points with which it is moving, that has to be greater than this CS. That means the velocity of the propagation of the perturbation itself. So if let's say this V is greater than CS, what will happen? So in some time this perturbation will move to Q, but since V is greater than V is greater than C, so what will happen? Q will move forward at that time, by that time, right? So at any instance P cannot have any effect on Q. So in that case it is asking that the flow is subsonic in choose the correct options. So Sumit, can you tell me which can be the correct option for this question?
I think number 3 is correct. P and Q are not causally connected.
Okay, so yes, correct. So first of all, this flow is subsonic in nature. This is not true because the velocity of the flow is greater than sound speed, so it should not be true. This is basically here, this is super
Sonic.
Now the second one is, the flow can be incompressible. Pressure perturbation does not lead to density fluctuation. Now if we remember that there is a discussion on the lecture series given by the professor. So there has been a demonstration that if the flow is subsonic in nature, we can consider it as a incompressible flow, because there has to be some calculation. Like what is the calculation is, let's say we can have del V by V. Now this might be basically what happens is that del rho by rho, this has to be less than 1 if it has to be incompressible, right? Because we
Yes.
tell that if there is no change in the density, then we tell that is a incompressible medium, right? So if the change in the density is very much smaller than the mean density, we can tell it as incompressible. Now to move on to this situation, we can start with some incompressibility. We can start with the less Mach number. Let's say m, if it is less than 1, right? Now that is possible only if this v is less than cs, right? So that is the case of subsonic, but here we are talking about the supersonic flow, right? So this cannot be considered as incompressible. Okay, now the third option is correct, as Sumit was suggesting, that as the propagation of this pressure perturbation is not sufficient enough, the velocity is not sufficient enough to reach the q, since the q has been moved to another point in that particular time, right? So this is p and q are not causally connected. This one will be a correct option. So yeah, Sumit was correct. So let me write the yeah. So now the next question is, consider 2 points. Now again, just like same thing. So consider 2 points p and q within a gas flowing with a constant velocity v as earlier. Now even though p and q are very far away, now this time what happens is, you have 2 points. Let's say you have p and let's say a very much q. This distance can be larger than this also, but I am just assigning that okay, this may be very much in a higher distance. Okay, now what is the question is telling is, still the pressure perturbation generated at p and can reach q. Now if the pressure perturbation generated at p has to move to this q, what will happen? So the pressure perturbations will be moving with a velocity, let's say cs, the sound speed, right? And this p and q, this will move with some velocity v. Now if this pressure perturbation has to reach this q, then what will be the case? That cs has to be greater than v, then only it can reach to q, right? So if this is the case, then what will be the nature of this flow? That will be the
Subsonic.
subsonic, correct. So now it is subsonic. Now the first option is telling that the pressure perturbation leads to density fluctuation. Now if it is subsonic, then just in the previous question we have discussed that if it is subsonic, then it will be incompressible, right? Incompressible. So if it is incompressible, then the density fluctuation, it might be there, but that should not be considerable, right? So we may consider that this first question, first option cannot be a possibility. Okay. Second one is the Mach number is very high. Now for subsonic flow, we don't have Mach number as high; it is quite low, right? If CS is less than greater than 1, then there should be m less than 1. So this is not also correct. Now P and Q are not causally connected. That is also not true, because this is going to affect this Q point. So this is also not true. Now what remains is none of the above. So in for this question we will have this 4 has to be correct for this question. Okay.
Yes.
Yeah. So fine. Okay, so the next question is, so we have 4 statements here, so pick the correct statements. Okay, so the pressure distribution on the surface of a non-spinning ball in an in-viscid fluid is asymmetric. So what we have is a ball and the fluid itself is in-viscid. Okay, what does it mean by in-viscid is there should not be any velocity gradient, right? Now you don't have velocity gradient, each layer is moving with a particular same velocity, and you don't impart any spin on the spherical ball. So it is asking that the pressure distribution on the surface of non-spinning ball in an in-viscid fluid is asymmetric. Now you see, if you don't give any velocity like this, you are not imparting any spin. So what will happen? And the fluid is inviscid. So as we discussed in previous classes, that if it is inviscid, then it will have only one velocity component that is moving towards this, right? There should not be any velocity component in this normal direction, correct? So what will happen is, so we don't have any rotationality here, so the ball is not going to rotate if it is inviscid. Now what will happen is, if you don't impart any spin, then there is no external force also to rotate the ball. Now the case is, if you don't have any velocity like this, and the velocity in this layer and this layer will be same, right? Now let's say in general, if it is V2 and this is V1, so you have V1 equals to V2 here. Now if you consider the Bernoulli's theorem, so what will happen? You have a half rho V1 square plus P1 equals to, let's say, half rho V2 square plus P2. Now have a look here, this V1 and V2 is same, right? So what will happen is P1 equals to P2. So is it asymmetric? No, this is a clearly symmetric, so this should not be a correct answer. Now the second question is that the pressure distribution on the surface of a non-spinning ball in an inviscid fluid is symmetric. Obviously, as we discussed in this, so this should be a correct answer, right, Sumit?
Yes. Yes. Yes.
So now the third option is in a highly viscous fluid. So for highly viscous fluid, what we have is, we have a Reynolds number, right? So Reynolds number is given as Re, which is like VL by some nu or eta, where this is coefficient of viscosity. Now if it is highly viscous fluid, what will happen is, this is pretty high, so that means this is less than 1, so this is low viscous, right? Low viscous fluid or low Reynolds number viscosity. Okay, so drag force on a solid object suddenly steeply decrease at a critical Reynolds number known as drag crisis. Now if you remember, there is a plot like this CD, there is a viscosity gradient, sorry, there is a drag coefficient, the CD will be the drag coefficient right? So there is a some plot, might be there is some this and this one, and suddenly it drops, and then something like that. So the Reynolds number increase in this region, right? So for low Reynolds number, as we found this, because this is low viscosity, sorry, this is high viscosity. Just a second, I have written some mistake here. This is high viscosity. So what we have for high viscosity, the Reynolds number should be very much low, and that is this regime, right? Let's say this regime. Now for this regime, you don't find any steep decrease. It is decreasing in a steady manner, in a gradual manner. Now if you look at this point, right, there is a steep decrease. Suddenly it falls up to some particular value, right? Now this is some critical point or critical Reynolds number at which the property of this drag coefficient is changing, right? So now the case is for this question is, this is happening in a very high Reynolds number situation. Now for high Reynolds number, you will have the low viscosity situation, right? So this third option, according to the discussion what we have, Sumit, can you tell me whether it is correct or wrong?
It is incorrect.
Yeah, it is incorrect, because we can tell that there is a low viscous fluid,
Low viscosity.
then it can steeply decrease at a critical Reynolds number. Yeah, so that should be a drag crisis, but this is not the case, because this is not a drag crisis is applicable for low viscous fluid. Now what we have as the fourth option is, drag crisis is due to fact of transition of laminar flow to a turbulent one in the thin boundary layer around solid surface. So whether this is correct?
Yes, this is correct.
Yeah. So drag crisis has one of two reasons. One of this is this transition of laminar flow to a turbulent one in the thin boundary layer around solid surface. So this is a low viscous fluid, so the streaking is not that much prominent, but there should be some streaking. And what happens is, in that thin boundary layer, you will find out some turbulence, and that is the reason of this drag crisis. Okay, so due to which the drag force suddenly decreases. So this fourth option is a correct one. So, okay. Now the next question is, here again we have some statements, we need to find out the correct statement. So intersection of characteristic straight lines for forward and backward waves leads to non-uniqueness of the solution in case of smaller perturbations. So we have so many keywords here. Let us underline everything. So there is a characteristic straight line for forward and backward waves leads to non-uniqueness. That means whether the solution is an unique one or not in case of smaller perturbation. So the perturbation we are talking about is smaller, because to have some waves we need some perturbation, right? And that perturbation is very much smaller in its amplitude. So what will happen is, first of all, what is the characteristic straight line? Now we have, sorry, this should be a proper straight line. So we have a t here and a x here. Okay, now what will happen is, there is a x equals to CST graph, right? And also you should have another line which will be like this, and that should be like x equals to minus CST. Okay, now what is happening is this one and this one, these are for forward and backward waves, and they are going to intersect at t equals to 0, right? Even if it is moving in a certain direction, let's say x equals to plus 5 or something, so at t equals to 0, that means at the initial time there has to be some intersection, right? Because it is generated from that particular point, so there should be some intersection between the forward and backward propagation, backward waves characteristic straight lines. These ones are called characteristic straight lines. Okay, so these are intersecting with them. Now that is not providing any non-uniqueness, right? So at this point we have only one velocity, and this is essential that if there is forward and backward propagating waves, they are going to generate from particular one location, so there should be the intersection of these characteristic straight lines, and that should not provide any non-uniqueness in the solution, right? Now the second option is that intersection of characteristic straight lines for forward and backward waves leads to uniqueness of the solution in case of smaller perturbation. Now this is correct, right? So yeah, so in case of smaller perturbation, right? Sumit, I think this should
Yes,
be a
yes,
correct
correct.
one. Yeah, someone is joining. Okay, so the second option is correct one. The third question is that, third option is that for larger perturbation, double valuedness of solution leads to formation of shocks. So for larger perturbation, what will happen is, so for smaller perturbation, what will happen? First of all, we have some periodic, sorry, this should not be distorted anyway. So what we have is, this way we have some wave profiles, right? So we should not have any distorted things. Now when we have larger perturbation, what will happen is, let's say you have these two profiles. Now you have larger perturbation, that means if the velocity at this point and this point, now this is v1 and this is v2, right? And somehow if v1 is greater than v2, right, instead of v1 equals to v2, for this is true for smaller perturbation. Okay, now if there is larger perturbation, this is the case, and now if it is this, so what will happen? This will move faster than this. So now we will find out that there is a possibility like this one, right? So what will happen in a particular time? You will have two two intersection like this, or three intersection. So this is called the double valuedness, which is not a good idea of any functionality. Okay, so if double valuedness is not a good thing, so what will happen is there should be a discontinuity, right, this way. So here you see this is like a pressure pass, and you have a discontinuity because this double valuedness cannot be steadily, okay, discontinuity. Someone is writing something. Oh yeah, Ravi Shankar. V1 V2 will intersect. Yeah, that's true. So that should not happen, right? Okay. So since that cannot be a possibility, because at a particular point you should have just one value of a velocity, and that should have a particular direction. So you cannot have this double valuedness, so it forms a discontinuity, and therefore that will generate a shock, because shock is just a discontinuity across which there is a sudden drop of pressure as well as density, as well as basically there is a drop of velocity, right? So this, for larger perturbation, double valuedness of solution leads to formation of shocks. That is true. Now the fourth option is two characteristics curves in Tx space, as we draw here, right? For forward waves cannot intersect each other irrespective of size of perturbation. Now tell me what is true about this. Ravi Shankar, Sumit.
Number 4 is correct, I think.
Why?
Forward waves cannot intersect with each other.
Forward waves cannot intersect with each other. Okay. Now, okay, fine. Ravi Shankar, do you have any comment? So writing something. Okay, so you are telling that two characteristics curves for forward waves cannot intersect with each other irrespective of size of perturbations. Okay. So you have a forward wave. Okay, yeah, it's true. So in any case it cannot intersect with each other, it is each other respective of size of perturbation. Fine, so this may be correct one. Fine. Now, okay, just a second. Okay. Next question is this one. So we have a pressure and density isocontours, right, are spherically distorted, and any pressure perturbation at any point on those concentric spheres can affect the equilibrium condition at any other point on those concentric spheres. Comment about the nature of background flow as discerned by Lagrangian as well as Eulerian observer respectively. Sumit, can you answer this question?
Yes, give me a second. can affect. Okay. Subsonic waves. It will be sonic and subsonic. Number 4,
So
I
for
think.
Lagrangian, it does not depend upon the velocity of the flow, right? So it will
Yes.
only depend upon the velocity of the perturbation,
Convention.
and that is always sonic of pressure perturbation. Now the second one is the about the Eulerian observer. So since this is affecting the other points equilibrium condition, so the the velocity of the propagation, sorry, velocity of propagation of the disturbances should be higher than the velocity of the flow itself, and that is possible only if this is a subsonic flow, right? So yeah, so this is just similar to the first question, but the words of the questions are little tweaked. So okay, this is a okay. Now the next question is, you have a set of coupled equation as follows. So which one is correct for this? Sumit, can you do it?
Mm-hmm. I am.
Yeah, have a try.
I think it should be number 3 because heat equation and wave equation are both 2D. I mean not 2D. I mean second order differential equations.
But you have a f1, you have a f, right?
Two.
So here you have
Okay.
a 1D equation for f1, and then you have a equation for f1 itself in terms of f, which already have some differentiation with that. So can it be, I mean, transformed to a particular 2D equation here,
Yes, 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 yes. Got it. Exactly.
right?
TFTX. TX. Describe. Describe equal to C. C squared. T squared. I think this looks like a wave equation to me now.
So
D
the
squared of dt
wave
square equal
equation.
to C squared d squared of dx square.
Okay, so how should I start is, let's see, have a del f1 del t, let it be calculated. So what we have is del 2f del t2, right, plus c del 2f, and then what, del t del x, right? This is a del, and what we have next is you have a del f1 del x to calculate, and that should have like del 2f del x del t plus c del 2f del x square, right? Now if we put this 2 in this, what will happen? So you have del 2f del t square plus c del 2f del t del x minus c del 2f del x del t minus c
square.
sorry, this is b
C square.
c is there, so this is square, so del 2f del x square equals to 0. Now these two terms will cancel out, right?
Cancel out. Yes.
So we are left with del 2f del t square, and if we just interchange the size, so it will be
C square del square of del x square.
Del x square. Now this is OF equation, right?
Yes.
OF equation. So this second one is the correct answer. Okay. Second. So it is second. Fine. Now the next equation is that, sorry, this one. Now you have a 1D advection equation where u is the 1D velocity, alpha will be conserved along a characteristic curve, which is, it's a equals to something.
Hello, sir.
Yes.
The screen is not visible there.
Screen is not visible?
No, I can see the screen. That's not a problem. Yes.
It's okay, right? Yeah, so he is saying that this is non-linear equation. No, this is non-linear. Not is non-linear. This is just OF equation. And screen is visible, right? So my screen is visible?
Yes, it is visible to me.
Okay. So our next question is this one, that consider the following 1D advection equation. So we have del alpha del t minus u del alpha del x equals to 0. So we have given a equation. Now what it is suggesting is, so alpha will be conserved along a characteristic curve A. Choose the correct form of function f x t. So how can we do this is, so we need alpha to be conserved along some characteristic curve which is given by A, right? So what we need to do is this del alpha del A has to be 0, right? If it is has to be conserved. So to do so, what we can do is del alpha del A, right? Sorry, just a second. So del alpha. Now a is depending upon x and t. So what I can do is del alpha del x del a plus del alpha del t, right? Del t and then del a has to be 0. Okay, now if we have this equation, this one,
Hello, sir.
yes,
Sir, this del alpha by del a equal to 0. Like,
Yeah.
which condition is it?
see, if you have to have a particular quantity conserved along certain characteristic curve which is given by some a, okay, so what it is telling is if you are moving along some curve like a, right, and then alpha is conserved along that curve, so if you are changing the value or if you are moving along, let's say you have a, let's say some curve, right, this is represented by a, for example. So if alpha is going to conserve along this line, what does that mean? Now the line is depending upon this parameter a, right? So if had this alpha has to conserve along this line, so we need some parameter, right, depending upon which the alpha can change, but we have just one parameter here which is a. So if the del alpha del a is itself 0, then it might it is telling that alpha will be conserved, right? So whenever we are taking certain things, conservation of something, so we already consider that there has to be some parameter depending on this alpha on which this alpha will depend. Now in these curves what will happen, the a is only parameter, so if alpha is not depending upon a, that should not be changed, that will be conserved. Okay, hello.
Oh, yes, sir. Okay.
Okay, so we have del alpha del x del a. Now if we just compare this equation, this one, with the given equation, so what we have is in the given equation is minus u del alpha del x plus del alpha del t, right? This is going to be 0. Now if we compare these two, what will happen? We will find out that there is a del x del a, right, equals to minus u, correct? This is one equation. What we have, say number it by a, and another is del t del a, that should be 1, right? So this is the equation b. Now using these two, what will happen is x equals to minus a u, okay? Or in the other way, what we can do is, just a second, yeah, so we can write it like this also, del a del x equals to minus 1 by u, okay? And now if we consider this, if we integrate this over this, so a is minus 1 by u dx, right? This will be some integration, and also since a also depends upon t, okay, so what will happen, we can consider a initial an additional term which will be depending upon only t. Let's say instead of f we may use g, because so this additional term, what it is telling is, so a is depending upon x as well as t. Now this term will give you the x dependence, so you should have some additional term which will depend upon t only. So what will happen is when you just integrate this in terms of x, so this gt over this del x will give you 0, only this term will remain, and that will give you the minus 1 by u. Okay, so this will give you basically minus x by what, u, right, plus g t. So this one is from a, means this number a, not the exact if in the question. Now if we go to b, what we have, del a del t, that should be 1. Okay, so alpha this time will be dt plus, also alpha is now depending upon x also, right? So we have fg function, so let's say we have a function of h of x. Okay, so what will happen, so alpha will be given by t plus h of x. Okay, so we have, let's say this is 1 and this is 2. We have two equations for alpha. Okay, sorry, we have two equations for just a second, there is some mistake.
That will be del alpha, del a by del t.
This is del a, yeah. This is a, this is also a. So we have two equations for a, and we need to find out a itself. So how can we do that is, let's say you have this a, right? So what you can do is, let's say del a del x, right? So if you do this, you will get h prime x. Fine. Now this del a del x is h prime x, and if you compare this with this equation, so what will happen is minus 1 by u, right? So you have this h prime x equals to minus 1 by u itself. Now if we put, just a second, let's say we have, omit these things right now. Yeah, so we left with this equation that h prime x is minus 1 by u, and you have this equation a equals to t plus hx. So if we write this in this way, so what will happen is, so you have a t, sorry, there has to be something, yeah. So you have h prime x equals to minus u, right? So using that you can also find out hx, right? What will be the minus x by u itself, correct? So now if we write it like a equals to t plus, so sorry, t plus hx is there, so this is be x by u, right? So this should be ut minus x. Okay, so there is some difficulties with the sign convention here. So basically what happens is that this will depend upon u, and also there will be a minus sign. So this will be a correct answer, this x minus ut. Okay, now instead of this, I ask you guys to calculate one, that instead of this del alpha del t minus u del alpha del x, if you have a plus sign here, what will happen? What will be the correct answer for that question? Using,
So then a will be in the plus, no? A will be x by u plus g of t. If it
it
is
will be
plus.
x plus u ut, right? Yeah, that will be the correct answer. So for this question we have x minus ut, and if it is plus, then that will give you a x plus ut kind of a information. Okay, so sorry, fine. Sumit, any problem?
No, that is okay.
Yeah. So yeah, so we have another problem here. So a horizontal cylindrical tube is divided into two parts by a diaphragm having different background pressures, say P1 and P0 of a diatomic gas. Now a hole is created in the diaphragm leading to flow of gas from P1 to P0 region. So first of all, what we have is the cylindrical tube, and within that we have a diaphragm. Let's say there is a hole within the diaphragm. So what will happen is here you have a P1, you have P0. So there is clearly a pressure difference, right? So as soon as there is a hole, there will be a flow from this P1 to P0 direction, right? So this will be the thing. Now this rupture of diaphragm leads to formation of forward as well as backward waves, fine. So when you are creating some disturbance in this region, so what will happen? So there will be some generation of waves also. Now if there is wave and if there is nothing to restrict the propagation of wave, then what will happen? The wave can go in either direction, right? It can go forward, it can go backward, right? The two possibilities are open for the perturbation to propagate. So now the quantities remaining conserved along forward and reverse characteristic curves from any arbitrary point in the region already reached out by waves have values of. So how do we calculate? So first of all, what is happening is, so if we try to find out the characteristic curve for this particular one, so what will happen is you have a x, right, and you have a, sorry, this will be x, this will be t, and the characteristic curve will look like there is a x equals to CST and another is this one which will be for reverse, x equals to minus CT, right? This will x equals to minus CT. Okay, so now what it tells is that we are considering a point where the wave is already reached out. Now which one should be the region in which we need to consider the point? Can anyone tell me? I mean, where should I pick a point? Whether this one, let's say this is one region, this is two region, and this is three region. This entire one in this within this cone is 3. So why should I pick a point such that the wave is already reached there? That means they are causally connected. So tell me, which region should I take the point?
Region 3.
Region 3. Yeah. So what happens is, for this region 3 you have,
Sir, why not region 2?
see, for region 2 you have a velocity of the flow which is higher than your propagation speed of perturbation. So if you have a higher flow, then what happens is 2 points within the flow cannot be causally connected, because if you generate perturbation at a particular point, it will go with some speed cs, and the flow is itself moving at some velocity v which is higher than cs. So as the perturbation is moving, the receiving point is also moving with a higher velocity than the perturbation itself. So you cannot reach that point ever, right? So that case,
Yes sir, I'm
yeah.
getting.
So we cannot choose this 1 or 2 regions. We can only choose the 3 regions. Now if we have P So what will happen? So in each region we can consider forward and backward characteristic curve. How? So we need to bridge out the two lines which will be parallel to forward and backward characteristic curves. So this one, as you see, this one, this is your forward, right? Why? Because this is parallel to this one, okay, and this is your backward, okay. Now in this, you see, this is just a shock tube problem where you don't have any piston, okay. So this is basically a problem where you can consider those J plus J minus as your conserved quantities, right? Now J plus J minus are the quantities which are given as this, like J plus minus is equals to U for the velocity of the flow itself, U by Cs, and then you have a plus minus 1 by gamma, and then P by P dou. P dou is basically the background pressure. Now here P1 and P0, those are two background pressures here, but P0 is a reference what we are taking, okay. Now we need to calculate this J plus and J minus. Where for forward propagating wave we should calculate the J plus. So for this one, what we have is, if this J plus is conserved, so what will happen? J plus is conserved along this line, okay, from P to, let's say, A. From P to A, PA, what will happen is this J plus is conserved. Fine, this is conserved.
So the first line equation is x equal to CT or SP? The first
This one?
line
This is suffix s. There is also suffix. This is also suffix s with CST. CS for sound speed. Okay. Let me rewrite it. So this is C suffix S for sound. CS is sound speed. Okay. These two are same, just a minus sign is there for reverse.
Yes, sir,
this is a forward. So J plus will be conserved along this PA. Now if we move to this point, what is happening is, here you don't have any value of T, correct? Now if we don't have any value of T, what will happen? We don't have value of U also, right? Because so if we have on this point, on this line, you don't have U is also 0, because that is the velocity, right? So if you U depends upon the slope, and when you are on this line, don't have the slope, it has to be 0. So now if U is 0, so what happens? J plus is just 1 by gamma. Now we are in this point, this A point. Now in this point, what will happen? In this region you have P pressure, this one, and here you have P naught pressure. So this is basically P1 by P naught, right? This J plus. So this should be conserved along this line. Now this one has to be conserved, right? And also for forward, this is J plus. Now for backward, what do we have? You have U by CS. Again, U is 0 because this is touching this, right? This is a B. So at point B, you will have J minus to be, sorry, U to be 0. So the first term will cancel out. Now the second term is minus 1 by gamma P by P naught. Now in this case, this is in this region where the pressure itself is P naught. So P naught by P naught will give you 1, right? P naught by P naught will give you 1, and that means this will be a minus 1 by gamma. Now we have two equation. First one is J plus is 1 by gamma equal P1 by P naught, right? Another version is J minus is minus 1 by gamma. Okay, now depending upon or having this concept, can you answer this question? Which one of the options are correct? Okay, another thing is here you don't know the gamma, right? But you know the gas we are considering is a diatomic gas. Now gamma is that Cp by Cv again. Okay, so you need to calculate the gamma for diatomic gas. If you know that, you know the answer.
Number 3.
Number 3, 5p1 by 7p0 minus 5 by 7. Why? Because gamma is 7 by 5, right?
7 by 5 is.
Yeah. So this is true. Anyone else is here? Yeah. So Ravi Shankar left the meeting. So okay. So here the answer is
Sir, here diatomic
Sir?
gamma, how did we calculate?
okay. So you don't know how to calculate gamma. Hello.
Oh, yes, sir.
Yeah. So let me tell me an example of diatomic gas. Oxygen.
O2, oxygen O2.
Yeah. So in oxygen what happens is there is two O, right, and they
yes,
are connected by some bond, right, in between them. Okay. Now let's say we started with some free particle. Okay. So and for generality we are considering 3D. So I have X, Y and Z. Okay. Now if this is a situation and you have a free particle, so what will happen? So at certain time, to have the total idea about this the particles motion, you need to know X, Y, Z, each one of them, right? You need all of this information. So
yes.
for a particle which is free, so you need 3 coordinates to know. Fine. Now if we understand the degree of freedom, what will happen? That there is a formula like gamma is 1 plus 2 by f. Okay, where f is the degree of freedom. Now for this one, so what will happen is 1 plus 2 by 3, right? This is the monoatomic gas also, right? We are considering just a one particle. This is there is no bond with one molecule to one atom to another
5 by
atom.
3.
So this is 5 by 3 for monoatomic gas. Okay. Now if we consider the diatomic gas, you see there is a bond, right? And as the oxygen molecule is moving, there has to be a constant on this motion. The constant is this bond length should be conserved. Okay.
So sir, degree of freedom will for O2 it will be 1 or
no? So you have two molecules, right? Sorry, you have two atoms. So for each atom, forget about the bond length initially. You have two atoms. So for each atom you have 3 degree of freedom if it is moving freely. So you have 2 atoms. So what will have? 3 into 2, right? This is total number of coordinates. You have to know about this thing. Now you have a constant like this. So you have a -1. Fine. So this is
yes, sir, correct,
this is 5. So this is the degree of freedom. Okay. Now you put this 5 in here. 1 plus 2 by 5. That will give you 7 by 5. Okay. So gamma will be,
yes sir, absolutely, I got it,
7 by 5. Yeah. So the third will be the correct answer. Okay, I hope it's clear.
Yes, sir. Clear.
Yeah. So the next question is, choose the correct statement about the shock formation. So again, so we have speed of object or background flow is less than speed of sound. So okay, let us go by one. So for shock formation, we need supersonic flows. So for supersonic flows, what we have is the speed of object or background flow has to be greater than speed of sound, right? Then only it is supersonic. So the first one cannot be a correct one. Okay. Now the speed of object or background flow is greater than speed of sound. Okay. So our background flow is greater than speed of sound. So this is correct. Okay. Now the pressure or density isocontours will be parallel to each other. Is it correct? Hello.
Yes, sir. It seems correct now.
No, I think. See, when the shock is forming, now when it is parallel to each other. So let's say you don't have any background flow. You only have the perturbation. Sorry, the drawing is not correct. So what happens is, these are all annulus having some certain radius. Like if it is r, this should be 2r, should be 3r. Everywhere it is symmetric or isotropic. So that is those isocontours when v equals to 0, right? Now here, in case of shock formation, what will happen? This v has to be greater than cs. It has some non-zero value which is very much high. Okay. In those cases, what happens is, you cannot have this parallel thing, because then those are distorted things, and those are distorted like this. So there is some intersection, correct? So if there is some intersection between the isocontours, they cannot be considered as parallel to each other. Okay. So shock formation only happens when there is
Sir,
certain.
under which condition is this? The second figure. Under which condition?
This one. This
yes.
one is, let's say, v greater than cs. Okay. Fine. So even if v is less than cs, there can be some, some intersection between these isocontours also, because basically there is some, there cannot be some intersection, but still, if v has certain positive value or non-zero value, then this isocontours will not be parallel to each other. Either they will intersect, and intersecting will be happening only if the v is greater than the sound speed. But if it is less than sound speed but greater than 0, it has non-zero value which is less than cs, then what will happen? Even if these isocontours are not intersecting with each other, but there should not be the symmetry or isotropy as shown in this, as tried to shown in this figure. This is not a good figure here. So consider this to all of them to parallel to each other when v equals to 0, but when v is less than 0, but v is greater than 0 but less than cs, then there has to be some non-isotropy or non-homogeneity in the isocontours, and they cannot be parallel to each other. So this will be not a correct answer. This will be not a thing. Now the last is,
sir, so for shock formation we won't get this symmetrical contour. We won't get for shock formation.
we don't get. Okay. So since the velocity of waves cannot be multi-valued at a certain spatial location, distorted profile of pressure pulse leads to discontinuity. This is again the same thing. So this is true, right? Because there is a multi-valued. So yeah. So this should be the correct answer. Okay. Who is joining?
So that forward wave case in that first example where V1 was greater than V2,
Mm-hmm.
that was also multi-valued, no?
Yes, yes, multi-value. So this will be 4. So okay, so this was the last question for today, and Anuj, you are too late for the class. It's running from 5. I've already completed today's questions. So Sumit, any problem?
No, no. So we are okay.
So Ravi Shankar,
Yes, sir. It is fine, sir. Got.
okay. So okay, so today's class is over. Now we can leave.